When it comes to communicating chemistry, there's a surface problem and a deeper problem. The surface problem is finding the right tool to communicate the chemistry. But the deeper issue is that our success as chemists is dependent on how well we communicate with others. The invisible barrier behind finding the right tool and communicating clearly to the other person is cognitive load. In this video, I'll explain the different levels of chemistry visualization, my favorite tools at each level, and how we used an interactive dynamic chemistry visualization to measure the impact we had at an outreach event. Stay until the end and I'll share my physics engine genesis with you so you can explore interactive dynamic chemistry systems too. When you think about it, it takes a lot of simplifying to get chemistry down into letters and lines. But two-dimensional representations like Lewis structures are the baseline for the written communication chemists exchange. Beyond writing these by hand, my favorite digital tool for creating Lewis structures is Alchemie. Alchemie has a really accessible interface that allows you to connect elements with lines and even do things like demonstrating how many electrons are being shared with each line. They're very useful for teaching students the written language of chemistry and communicating specific isolated structures. But whether you're speaking to reviewers, students, industry collaborators, or the public, two-dimensional blueprints can create a lot of cognitive load. Each step that we take to simplify the structures down into letters and lines requires the audience to recreate those steps using their imagination. So the next natural step is let's take this two-dimensional representation and make it three-dimensional. My favorite tool for this is MolView. I love that you can search or draw structures in MolView, and then on the right-hand panel, you can see these in 3D. With these tools, you can then understand the depth and space that an isolated structure occupies. But they still require the audience to imagine what these structures would look like interacting with other chemical species. This is where 3D animations really shine. 3D animation allows us to add the dimension of time to these structures. So here we can start to externalize the imagination process of how chemical species interact with one another. My favorite tool for creating these 3D animations is Blender, mostly because you can import a PDB structure and then animate it yourself. In fact, our most popular content is tutorials around how to use Blender and other tools to visualize chemistry reactions. So while it's clear a lot of people want to learn this skill, I can also tell you that it is extremely time-intensive to learn how to animate chemistry in 3D. Beyond just learning the software and the skill of how to visualize these chemical reactions, these animations are made using keyframing. The way this works is that you have your starting scene where everything begins. You move forward a second in time using keyframing, and at that 1 second, you restructure all the visuals to look as they should 1 second into the animation. So that includes moving all the atom spheres, any electrons that you have involved in the chemical reaction, and a lot more, depending on how complex your animation is. As you can imagine, this takes forever to do, and to do it well. And even at the end of it all, when you have your beautiful animation, it is still just a video. It's really hard to measure the impact of what the audience is viewing on their understanding. Enter the world of dynamic simulations. Some of my favorite simulations have been created by PhET at the University of Colorado Boulder. Here, the user has a direct role in the cause and effect and testing different variables and measures as they're interacting with the simulation. These simulations are great for developing an understanding of very specific concepts, like the ideal gas law. But what if we could take it one step further? By programming physics engines with chemistry logic, like valence or electronegativity, we can allow the engine to reliably display the underlying physics of a chemical reaction, but allow the user to direct interactions in the context of broader chemical systems. This would allow your students, reviewers, and the public to spawn chemical structures, watch how they interact with one another, and develop an intuitive sense of different types of mechanisms. What's more is that because these simulations are interactive, meaning that they drive the cause and effect, each mouse click becomes a data point that we can use to measure the engagement and impact of the simulation. These simulations can then be recorded as an animation or as a still for papers, talks, lessons, journal covers, and other resources. At the last ACS Kids Zone in Atlanta, we continued our 3-year collaboration with the outreach coordinators to create a dynamic simulation around the chemistry of slime. We wanted to give a broad audience the opportunity to explore computational chemistry in a way that felt accessible and engaging. These were the results. 167 total visitors, 87 unique players scanned the QR code to access the dynamic simulation. This suggests that a few of our players decided to come back and play again. On average, users spent 2 minutes and 33 seconds interacting with the simulation, which is considerable given that this was at a fairly chaotic, very packed, high-energy outreach experience. 5 dedicated players even beat the game, successfully creating slime by adding the right balance of borate to PVA, alongside actually making the slime, with chemists explaining the bond breaker chemical connector mechanism that underlies slime's gooiness. We were able to measure pre-post a shift from using sensory terms like gooey, wet, stretchy, to using chemistry terminology like polymer, borate, bond breaker, acetic acid, and hydrogen bonds. Of the 70 index cards we collected, only 6 used chemistry-based terms in the pre-assessment. In the post, 30 used mechanistic chemistry language to explain why slime is stretchy. This is a 400% increase. And not to brag, but our activity won the Kids' Choice Award too. If you want to try our interactive 3D chemistry simulation, just comment the word Genesis below and I'll send you the link. If you're a researcher, educator, or science communicator interested in developing a 3D visualization for your audience, please feel free to reach out. I'd love to collaborate with you.